In mathematics, a measurable cardinal is a certain kind of large cardinal number. In order to define the concept, one introduces a two-valued measure on a cardinal kappa, or more generally on any set. For a cardinal kappa, it can be described as a subdivision of all of its subsets into large and small sets such that kappa itself is large, and all singletons, alpha kappa are small, complements of small sets are large and vice versa. The intersection of fewer than kappa large sets is again large. It turns out that uncountable cardinals endowed with a two-valued measure are large cardinals whose existence cannot be proved from ZFC. The concept of a measurable cardinal was introduced by Stanislaw Ulam in 1930. Definition. Formally, a measurable cardinal is an uncountable cardinal number kappa such that there exists a kappa additive, non-trivial, 0 to 1 valued measure on the power set of kappa. Equivalently, kappa as measurable means that it is the critical point of a non-trivial elementary embedding of the universe V into a transitive class M. This equivalence is due to Jerome Keisler and Dana Scott, and uses the ultra-power construction from model theory. Since V is a proper class, a technical problem that is not usually present when considering ultra-powers needs to be addressed by what is now called Scott's trick. Equivalently, kappa is a measurable cardinal if and only if it is an uncountable cardinal with a kappa-complete, non-principal ultrafilter. Again, this means that the intersection of any strictly less than kappa many sets in the ultrafilter is also in the ultrafilter properties. Although it follows from ZFC that every measurable cardinal is inaccessible, it is consistent with ZF that a measurable cardinal can be a successor cardinal. It follows from ZF plus axiom of determinacy that omega-1 is measurable, and that every subset of omega-1 contains or is disjoint from a closed and unbounded subset. Ulam showed that the smallest cardinal kappa that admits a non-trivial countably additive two-valued measure must in fact admit a kappa additive measure. From there, one can prove that the least such cardinal must be inaccessible. It is trivial to note that if kappa admits a non-trivial kappa additive measure, then kappa must be regular. Finally, if lambda less than kappa, then it can't be the case that kappa 2 lambda. If this were the case, then we could identify kappa with some collection of 0 to 1 sequences of length lambda for each position in the sequence. Either the subset of sequences with 1 in that position or the subset with 0 in that position would have to have measure 1. The intersection of these lambda many measure 1 subsets would thus also have to have measure 1, but it would contain exactly one sequence, which would contradict the non-triviality of the measure. Thus, assuming the axiom of choice, we can infer that kappa is a strong limit cardinal, which completes the proof of its inaccessibility. If kappa is measurable and PV kappa and M satisfies psi, then the set of alpha less than kappa such that V satisfies psi is stationary in kappa. In particular, if psi is a pi1 formula and V satisfies psi, then M satisfies it and thus V satisfies psi for a stationary set of alpha less than kappa. This property can be used to show that kappa is a limit of most types of large cardinals which are weaker than measurable. Notice that the ultrafilter or measure which witnesses that kappa is measurable cannot be in M, since the smallest such measurable cardinal would have to have another such below it, which is impossible. Every measurable cardinal kappa is a zero huge cardinal because kappa mm, that is, every function from kappa to M is in M. Consequently, V kappa plus 1m, real-valued measurable. A cardinal kappa is called real-valued measurable if there is a kappa additive probability measure on the power set of kappa which vanishes on singletons. Real-valued measurable cardinals were introduced by Stefan Banach. Banach and Kuratowski showed that the continuum hypothesis implies that is not real-valued measurable. Stanislaw Ulam showed that real-valued measurable cardinals are weakly inaccessible. All measurable cardinals are real-valued measurable, and a real-valued measurable cardinal kappa is measurable if and only if kappa is greater than Thus a cardinal is measurable if and only if it is real-valued measurable and strongly inaccessible. A real-valued measurable cardinal less than or equal to exists if and only if there is a countably additive extension of the Lebesgue measure to all sets of real numbers if and only if there is an atomless probability measure on the power set of some non-empty set. Solovay showed that existence of measurable cardinals in ZFC, real-valued measurable cardinals in ZFC, and measurable cardinals in ZF are equiconsistent.